We're going to talk about silver bullets. Okay, I'm going to start with the expected introduction slide. My name is Klaus Iglberger, and you might know me as the guy who talks about design, software design, design patterns. And why do I do this? Well, probably because there's so few other people that actually want to do this. So I just talk about C++ and do trainings, consultancy. This is pretty much what I do for a living. So let's talk about silver bullets indeed. And in order to warm up a little bit, let's take a look at a simple example. And so, if you know me, if you have been to any of my talks before, you know that I have kind of a go-to problem. And please don't complain. Yes, we are gonna draw shapes again. It's simple, it's a little boring. Because it's simple, it's also really easy to follow. And we're gonna see a couple of solutions today. So I think a simple example is way better than anything more complicated. Let's introduce a couple of requirements. So we'll start, and you'll only see shapes and circles and squares. But eventually, I also want to have rectangles, perhaps ellipses, potentially many more kinds of shapes. So this system should be extensible by new kinds of shapes. Good. Also, let's assume that this is not just a small, tiny project, but something big, because this is where things get interesting. So let's assume this is at least 10 million lines of code. And not just done something by a few developers. Let's say this is a project that really needs to scale, 100 developers, potentially more. All right, drawing shapes. This is how we could do it. So I might just start with a shape base class. It's a traditional, good old base class with a virtual structure and a pure virtual draw function. Yeah, the example is simple. There may be a few more virtual functions. Perhaps we have an export to JSON in this class. Perhaps we have a serialization function. There may be more. And of course, draw might take a couple of parameters. It doesn't have to not take anything. It's a simple example for a shape-based class. Now, of course, derived classes implement the shape-based class. The circle, it's a really basic circle. It has a radius, perhaps a center point, a couple of stuff. But it now has to implement this draw function. It has to. It's a pure virtual function. But it doesn't really want to. The circle does not want to couple to graphics libraries. It doesn't want to know about OpenGL, about 3DX, about any of these details. Therefore, we should externalize this properly. And one very common solution is to externalize this with a strategy design pattern. So we introduce a base class called drawStrategy, templated on a concrete shape type. This could be circle or square. And this is pretty much the abstraction of drawing. So the circle, now in its constructor, accepts a draw strategy, right here. A unique pointer to a draw strategy, a pointer to base. Moves this into its data member of the same type. And now, whenever somebody calls draw, we just delegate. We delegate to the draw strategy, which now knows what needs to be done. And a circle doesn't have to know. Great. Yeah, it's decoupled, OpenGL, 3DX, all is possible without the circle knowing. Okay, so that circle does not feel so lonely. There's also square, but it's pretty much doing the same thing. Square also takes a draw strategy, now one for square, stores it, and whenever somebody calls draw, it just calls draw. Good. So now that we have potentially also many more shapes, we want to have a lot of them, many of them. Therefore, what we would do is we would potentially at least have a vector of shape pointers. Well, that's what we usually do, right? So we have a vector of unique point of shape. Because this is quite a long type, quite a mouthful, we just abbreviate this, call it shapes. But then, now it gets even better. There is a shapes factory. Ooh, factory. So this shape factory takes some... Oh, okay, we're back. Takes a some file and extracts all the shapes. Yet it's again an interface. So this is a pure virtual function. It needs to be implemented elsewhere. Then I have a draw shapes function, which allows me to just traverse a vector of shapes and to draw all of them. Okay, that's fairly simple. And in addition, there is a create and draw shapes function, taking a factory, some file name, and it uses the factory to create the shapes and to draw all of the shapes created. Nice. So at this point, we're in a position to really start to add details like how to draw. Okay, to be a little bit neutral, I choose the OpenGL drawer, implementing the details for circles and squares. And so essentially just implementing the two draw functions, well, the one for circle and one for square, doing some real work. Good. And then, of course, we also need some kind of factory. Okay, your shape factory. Please don't read all of this code. Definitely not. This is just a wall of code, but we implement this create function. We extract circles, squares, and of course, potentially other shapes from the file and put them into this vector. Sure, we make unique a square, and we add some draw behavior, like the OpenGL drawer. Okay, and then you're good to go. Then in the main function, we create a factory, we pass it to the create and draw shapes function, and this will work. Great. And you see, this is modern C++, right? So if you now paid attention, oh, one thing in between. Sure, of course. I said it's something that we want to extend. So let me add this line, this architectural boundary. So above this line, this is the high level, the abstract stuff, the base classes, the things that don't need to know about details. And below is the low level. That's where all the details are. Yeah? That we choose OpenGL, that we extract from this particular file format, etc., etc. Okay, some people are confused. Okay, way too much detail. Okay, let's call this my code and your code. So my code is above the line, your code is below the line. And you would like to add different other kinds of shapes. Rectangles, for instance. Great. So again, don't read the code. It's the same thing again. Yeah? A rectangle taking some draw strategy. You could also extend the behavior for drawing, of course. And last but not least, you could extract rectangles as well. Meaning, in other words, it just works flawlessly. But now, you've paid attention, and so you realize this is quite a modern C++ solution, right? Unique pointers. Yay, no memory leaks, so much better. There's a move semantics. Haha, nice. There's an override. Yeah, you should use override, you know that, modern C++. Look here, there's an equal default. Whoa, better than writing the stuff yourself. There's an auto in a range-based for loop. Whoa, and there's a string view. Really a wonderful modern C++ solution. Amazing. Okay, I actually expected some kind of reaction, something. I know it's the last session. I expect happiness. Way, yeah. But you're looking very skeptical. This is kind of the expression. This is like, Klaus, really? Seriously? And some of you look even worse. So you might look a little shocked. Okay, look, these two guys in the first row, they even lost their hair. Okay, I totally agree. This might not be what we're doing anymore today. Some of you truly are unhappy about the style of programming. The style that, we could even give it a name, this is what we call the Gang of Four style. Named after this book, pretty much, the so-called Gang of Four book, which you probably all have seen, or at least touched. Yeah, perhaps even taking a look inside. The classic book on design patterns. So let's call this the Gang of Four, the GOF style. You're unhappy about this. You are, because you realize that what I've just showed may contain a couple of, in quotes, modern C++ features. But this is not really modern C++. This is old style. This is 1996, perhaps 1994. I think the book was 1994, sorry. But still, this feels really old. And realize that, you realize here that you don't want to use this anymore. But let's face it. I claim, without any proof, because this is not really something that I could prove, that 90% at least of all projects use this style of programming. This is not something of the past. This is very much what we do today, the art of programming. And yes, of course, you here at the conference, you're the people that are above this already, because you care about your level of C++. You care about looking further, about improving stuff. But we're in a bubble. We're in this little bubble of 10% at tops. We know that there is new stuff, better stuff today. And so, well, if you truly want this to change, sure, people like me can give talks about this. People can actually say there's other things today. But in the end, I think it's you. In the end, I believe you will have to continue and help to spread this news. So, you have coworkers, right? And I know you're top-notch, but your coworkers, so you might want to tell them that there is this new stuff. And this is indeed not news. This is why news is in quotes. You might have seen, or at least heard about this talk from 2013, more than 10 years ago. Jon Kalb's Inheritance is the Base Class of Evil. The title kind of already suggests that this might not really be the optimal way to do things anymore. And I should actually say that in this talk here, which sounds funny, which is not supposed to be funny, for just 3 to 4 minutes he complains about inheritance and then he shows something else. But still, there are many talks that kind of go into that same direction. Phil Nash, for instance, used this popular theme to say object-oriented considered harmful. Or Jon Kalb, in a Back to Basics talk in 2019, actually started with a slide entitled, "Why are so many developers hating object-oriented programming?" And explicitly stated, this is now exactly what he said, object-oriented programming is not what the cool kids are doing in C++. They're doing things at compile time. Functional programming, object-oriented programming, this is so 90s. And indeed, there are many more people. There's actually people that also proclaim object-oriented programming is dead right away. OOP is dead, long live data-oriented design. And some people want to get rid of virtual functions, using modern C++ to eliminate virtual functions, which I believe sounds a little aggressive, but it's pretty much a message. So there seems to be a theme here. Indeed, a common theme. Now, 2 years ago, I submitted a talk about design patterns, and once people see the term design patterns, they think object-oriented programming, and so unsurprisingly, I got this review. I believe that object-oriented programming, and essentially its theory, is overestimated. C++ always had templates, and now also has std variant, which makes most of the use of inheritance unnecessary. So, let's redo this. Let's do some real modern C++, shall we? Of course. So, let's go ahead and refactor this into a variant-based solution. All right. Let's start with circles and squares again. This is the circle class. And of course, you know something. There's no base class. There's no draw inside. Same for square. No base class, no drawing. Pretty much this is a very, very simple geometric primitive, nothing else. Good. That's pretty much what a circle and a square should be. Geometric primitives, no coupling to anything else. So, no inheritance, no dependency on graphics code, no pointers, which is nice. I don't need any base pointers to some shape-based class. As you will see, there's also no explicit lifetime management, making things easier. And that's just less code to write. No boilerplate code. Okay, which is a funny thing to say in C++. There's always boilerplate to some extent, but it's definitely better than before. So much simpler. And then here, pretty much a beautiful line. We now use std variant. This variant now stores the different shape types. Circles, squares, rectangles. Of course, there could be more. And so this is now an abstraction of different kinds of shapes. And so I call it shape. That's a shape. And what are many shapes? Well, shapes, plural. A vector of shape objects. I mean, objects, values. Not pointers to shapes anymore, but values. which is very natural, which is very intuitive, very nice. Good. Then the shapes factory. It's pretty much just doing the same thing as before, but again, note, no base class, no inheritance, no virtual functions, just does the thing that it has done before. And again, please don't read the code. But you also notice the one detail that I know feels is quite impressive. We don't make unique anymore. We just create a circle and put it in the vector. Yeah, it's stored inside one of these variants, but there is no need to dynamically allocate, which is great, especially for those who cannot use dynamic allocation. Okay, another variant. Oh, why not? I can use and want to use an abstraction of different kinds of factories. So let's create the abstraction factory, which is a collection of the different forms of factory. Good. And then, last but not least, the OpenGL drawer. Okay, again, this is the class that just draws all the different shapes. Again, no inheritance necessary, no virtual functions, just a class that does its job. Still, nicely encapsulating all the details about how to do things in OpenGL. And then, well, yet another opportunity. Yes, another variant to abstract from the different drawers. Let's call it drawer. Oh, yes, I see. This is what you like. Okay, and then the rest, the draw all shapes. This is actually really good. You will not stop smiling for the rest of the day if you see this. See, the visit function takes two variants. A drawer, just some abstract variant for drawer, and some shape, any kind of shape, circles, squares, whatever. And yes, what this is doing is actually multi-dispatch. Try that with virtual functions. Oh, this is not fun. But here, it's a line of code. Amazing! Okay, then create and draw shapes. Again, using std_visit, which is kind of expected. And then last but not least, all of this is just packed into the main function. A factory, a drawer, and I did create all of this stuff. Nice. So much better, isn't it? So much better. So first, no inheritance anywhere. It's a more functional approach. Talk about this a little more. Definitely no base class, no inheritance. No pointers, and no smart pointers either, anywhere in the solution. It's just values. We have still proper management of graphics code. Good. Everything's still properly encapsulated. And you probably also admire this elegant lifetime management. It's values. There's hardly anything to do. We don't need the unique pointers. And something that is a little hard to follow, but perhaps you get the feeling, less code to write. The boilerplate code is gone. Pretty much you're focusing on the things that need to be written. Nice. And so I would say it's so much simpler. Yeah, you're looking a little skeptical to some extent, but do not confuse simple with unfamiliar. Simple, it is simple indeed, but perhaps you've not used it before. And so once you use that, you will definitely agree, simpler. And here comes the best of it, it might even be faster. Ooh. Yes, and I've done it again. I've mentioned fast in a talk at a C++ conference. This is always dangerous. Because now people are looking at me and thinking, okay, fast. Challenge accepted. How fast is it? Okay. The problem is if I now give you some results, there's at least, out of this crowd, there's at least 10 people who will complain. At least. Yeah, and if you're not complaining today, because I might be a little intimidating at least, then you complain on YouTube. So, okay, let me show some performance results, but only under one condition. One condition only. Do you promise that you will not complain about my performance results? Okay, I've seen a lot of hands, I've not seen all hands. So if you, at this point, do not promise, then I have a solution. Close your eyes for about 20 seconds, and then everything is okay too. Okay? So, either you've promised or you close your eyes. Okay, here they are. So, very quick. I use 6 different kinds of shapes, not really important. I randomly create shapes, so the compiler cannot anticipate too much. And I do a simple operation, definitely not drawing, something that is pretty much the same for all kinds of shapes. This means that although it's random, it should still do pretty much the same work. And this is the two compilers I used and the machine that I own. So, now, performance numbers. The classic object-oriented approach that I showed first, this is the performance. Stewart variant, this performance. Yes, now everybody says, oh, GCC is so much better. Not the point. This is why I throw in the impact variant where everything equals out. Whatever. The point is, much faster, isn't it? Much faster. And immediately your C++ heart goes wide and say, I love this variant. Whoa. And so even the ancients have sung songs about variant. One feature to save them all, one feature to enlighten them, one feature to bring them all, and in C++ heaven, bind them. Or similar. But still, it's amazing, isn't it? And there's no surprise here. Absolutely no surprise. This is pretty much what people are telling us. Look here, closely, to what Jon Kalb said before. The cool kids, they're doing functional programming. Here it is. Other people, Phil Nash, functional C++ for fun and profit. Apparently it's fun and there's something to gain here. Or also, of course, Kevin Henney, who talks about functional C++. And Victor, who's here, and I thought he might like this, but now he's not in this room. The imperatives must go. Many talks about functional C++ programming. Whoa, amazing, right? And of course, once I've now told you, you have big plans. You have now a very big thing to do next week, because this week is meeting C++. Next week, you're going to go and refactor the entire code base. Now, you replace all these nasty inheritance hierarchies with Stewart variant. Yay! But wait, before you do this, we should actually take a closer look at this solution. We've not really distributed work right. So again, let me just draw an architectural boundary. Where should this go? Well, these two functions most definitely are my code. Now, I want to use them. This is what pretty much use the abstractions. Okay, so let's start by drawing this architecture boundary right here. Again, above my code, below your code. Okay. But wait, okay. Then your code is a little small, just the main function. Of course, I have to refactor a little bit. I have to move code. That is your code. The OpenGL drawer most definitely is your code, because I don't care about OpenGL. You might, I do not. So this goes into your code. Good. But then I need the abstraction. Okay, I was too quick. I just take it back. Drawer is my code because, sure, I need to use that. Now I know about your OpenGL drawer. I shouldn't know about your OpenGL drawer, right? And you might just start to realize this might not really work after all. I know it doesn't. You should realize there's a lot of coupling going on now. Yeah, sure, it's an abstraction to have a drawer, but what it could be is visible right here in this code. I see it. So there is coupling going on here to the explicit implementations. And this is terrible. This is really terrible from an architectural point of view. So from an architectural point of view, this is a total failure. There is no architecture at this point. Everything is coupled together. Everything is just one piece of code. And changing something might actually require you to change everything everywhere. Whoa, this is bad. And perhaps the reason why the other ancients have sung a different song about variant. One feature to fool them all. One feature to blind them. One feature to bring them all. And with dependencies, bind them. Thank you. So, but unexpected, but thank you. But now you think, wait, this cannot be. Standard variant is lovely, it's beautiful. There must be a solution here. I think there is. This was in the review, we've just forgotten about this. C+ has always had templates and variant. Templates. Now, of course, we could just throw a couple of templates at the problem. For instance, the draw all shapes function and also create and draw shapes, they could be function templates. If you make these two function templates, then actually we achieve what we are looking for, an inversion of dependencies. I no longer have to know about what kind of variant you provide to me, because I just take a vector of variants. Yeah, of course, concepts. I kept it short. So then I can just visit the thing, whatever I get. Nice. And the same for create and draw shapes. Again, we can invert dependencies. So I now no longer depend on your code. You can just give me anything. And it works. The shape abstraction now is really in your hands. I don't need to know about this anymore. Because I don't need to know about this shape abstraction anymore. If you want to, you can just introduce a kind of shape, a rectangle. So this rectangle is now just added to the variant, and you have more shapes. Good. Okay. The shapes factory, well, it's yours. You change it, you add whatever you need to. I don't care. Just the same for the OpenGL drawer. The OpenGL drawer just gets a new function. You implement how rectangles are drawn. Great. I don't care. It's in your code. It works. Suddenly it works. And yeah, I don't see you celebrate. And probably you shouldn't. Because the problem here is could be quite a big one. I said initially, this is a big code base, everywhere. Yeah, so at least I said 10 million lines of code, 100 plus developers. What I've now pretty much suggested is that we just implement everything in terms of templates. Any abstraction is now resolved by means of these templates. And what do we have in the end? Indeed, a 10 million lines header-only template library. This is fun. From a compile time point of view, fun for you, because while it is compiling, you can raise a family. This is not really what we want to have in the end. So, yeah, I'm pretty skeptical whether this will solve the problem for real. But this is the point. Standard variant might have a couple of really nice properties, but it just cannot solve all the problems. There is just no solution for that you can use everywhere. It doesn't exist. Probably should exist. We would like this, but it's not that easy. Standard variant just is not a replacement for virtual functions. Never has been, never was intended to be one. And still people suggest this from time to time. That's unfortunate. Standard variant pretty much is the antipode of virtual functions. It's at the other end of the design spectrum. And so to show a little bit what I have in mind here, let's just compare quickly. Left standard variant, right virtual functions representing object-oriented programming in general. So first, also something that is a little confused sometimes, both are fair and square dynamic polymorphism. Now, what you store inside a variant is something that you can only know at runtime. But standard variant is pretty much the idea of functional programming. I wouldn't say it's pure functional programming, but it pretty much is inspired from this direction. Whereas virtual functions, fair and square, are object-oriented programming. Standard variant and virtual functions, therefore, pretty much have kind of the opposite properties. A variant fixes your set of types that it can work on. It's quite visible in the variant type itself. But as a good thing, you have a totally open set of operations. Whatever you want to run on these types, you can add this freely without changing any existing code. But object-oriented programming is kind of exactly the opposite. You work with an open set of types. Anybody can add new types. But you have a limited set of virtual functions. So you're working with a limited set of operations. It's the opposite. And so you hopefully realize both of these have architectural properties, and they matter. You cannot just replace one with the other without changing pretty much the entire dependency structure between those things. So that's my personal opinion, but hopefully many people agree. I'm very much certain that the design plays a much more central role to the success of a project than any feature could ever do. Absolutely. And so just perhaps as a thing to think about, have you ever heard of a project that failed because you could not use some feature? Not really, right? But then perhaps the other way around. Have you happened to work in a project with a complete architectural document, perhaps even including architectural decision records, ADRs? Yeah, that's my impression as well. Perhaps some of you were nodding, but most people probably say, not really. And I think this is some kind of a culture in C++. In C++, features and language details have a much, much higher priority, apparently. They are kind of at the center of attention. You're mostly talking about how this feature works, how this code can be implemented. But we very rarely actually talk about design, how things should relate to each other, how things should be organized. And just as an example, I tried to do a fair comparison of this conference. To my best observation, 6 out of 48 talks, 48 in total, are related to software design, which is a 12.5%. And a 6 is with a question mark because you never know. Some titles are like, could be, don't have to be. So around 6 talks only. But the things that, however, is decisive for the success of a project, something missing. Okay, but now, of course, there are two kinds of people. So there's, of course, the people that say, oh, wait, I like variants so much, can I just use it? Of course. And I definitely didn't say that it's wrong or bad, not at all. It is beautiful. It just has certain architectural properties that you should know about. So if you use that, if you make a conscious decision, then document this. Document this by an architectural decision record and say, why did you choose a variant in this context? And so later, people can revisit this and can say, okay, it was just a performance thing, so perhaps we can revert it again. Yeah, if some extendability suddenly does not work well anymore. But this should really be done because you have chosen or made an architectural decision. But then there's the other people. The other people that now realize that perhaps variant is not the thing after all. Whew, I know your word. Klaus, does this mean that we still have to use subject-oriented programming? Really? We have to go back to this first example? Not really, no. Last year, so you're thinking about this talk again, of course, yeah? You're thinking about inheritance-based class of evil, that we should not do it anymore. But last year, actually, the closing keynote might actually have given a pretty good answer. So last year's last keynote, the closing keynote was from Ivan Kukic, who talked about progressive C++. And that's one of the first slides in his intro, where he's pretty much explaining what C++ could be described somewhere on, say, Wikipedia, in somewhere in the future. So let me just read that. Proc C++ is a broad genre of C++ code. The style was an emergence of psychedelic developers who abandoned standard C with classes traditions in favor of instrumentation and compositional techniques more frequently associated with generic, functional, or value-based object-oriented coding practices. Oh, value-based object-oriented coding practices. That sounds interesting. Okay, there's one thing that I want to do first before showing what you actually might have in mind here. So, how do you feel? Are you also kind of tired about the term modern C++? Do you kind of feel that after 13 years, you cannot really be modern anymore when you're more than 30, right? Do you perhaps also feel that this term is pretty much misused for all kinds of solutions nowadays? Oh, this is modern, this is modern, oh, this is modern too. Do you feel that sometimes? Oh, I definitely feel this a lot. I think modern C++ is not about features. No, it's about standards. I think it's about a philosophy. How to use the language, what we do today, how we approach the problems. And so I think we should actually rename that. And I have a great suggestion, which is not mine. No, I come back to this term that Ivan Kukic proposed, progressive C++. And if this is too long for you, proc C++. This sounds nice, doesn't it? Okay, I see, you have to get used to this term yet. But then, this evening, spell it out a couple of times. I'm using progressive C++, This sounds good, this sounds great. And suddenly we are perhaps in a new era. And so, I want to say thank you explicitly to Ivan. Thank you, Ivan, for giving us this term, because I believe this is a good one. But now, how could this progressive C++ look like? Value-based object-oriented programming. So let me show you. And it's not a terrible lot of code. It's actually rather simple. So I start with this shape base class and the deriving circle class. And it's the same code as before. No worries, nothing new, exactly the same code. So the first thing that I'm doing is seemingly random and doesn't make a lot of sense. It will make sense, but let's just rename the shape base class to shape concept. So yeah, I know, right now it doesn't make a lot of sense, but wait for it. Then what I'm doing is I'm actually introducing another derived class. Let's call this shape model. So what is this shape model? Well, shape model inherits from this shape concept. Okay. But it's not just some class, it's a class template, templated on a concrete shape type. So let's get a concrete shape. It could be circle, it could be square, rectangle, any kind of concrete shape type. And the shape model stores a concrete shape. It stores a circle, a square, etc. And, of course, last but not least, it implements that desired behavior, the draw. Which now raises the question, how does it draw a shape? We might just know that it's a concrete shape, but how do we draw it for real? Well, at this point, we cannot really do anything, so we delegate. For instance, by again using the design pattern I've shown before, by using strategy, just in terms of a template parameter perhaps. So in addition to the concrete shape, we also get a draw strategy. In the constructor, we get one instance of that, we store it, and now, when somebody calls this draw, we draw by means of this strategy. So again, we decouple, the drawing details are elsewhere, we don't have to really care about this right here. Good. Then, the circle class actually doesn't have to inherit from the shape concept anymore. So we can just get rid of the base class. And with this, of course, also with all the things that we actually don't really want to have in the circle, like the drawing. And so the circle becomes the simple geometric primitive you've seen before. Same thing as before, the same class that you've seen with variant. And because it's decoupled, I not just put it first. Doesn't matter. Can be first, can be last, doesn't matter, it's independent. All right, and so in here, I now pretty much encapsulate the polymorphic behavior of drawing a shape. The shape model is the class that knows how to draw a shape by means of this strategy. So it wraps this, the polymorphic wrapper around the concrete shape type. So, it's still not a value, I know. Next step. So let's put this into another class. Yeah, I know. The entire little hierarchy, the shape concept, the shape model, let's put this into a class that I now call shape again. The shape concept and shape model now in the private section. which I know, again, initially doesn't make a lot of sense. Now I cannot use it anymore. What's the point? Wait for it. Because the only place that I can use this is in this class. This is where I'm going to use it. And so what I'm now storing inside is just a unique pointer to a shape concept. A pointer to base inside the class. So yeah, sure, classic object-oriented programming, but hidden, nicely hidden inside a class, and we don't have to really know about this anymore. The only thing that now really is missing is that we update this class into anything that the value needs. First, of course, we need to create one of these. So let's add a constructor, a templated constructor. Constructor that takes any kind of shape, any kind of draw strategy, so any kind of implementation detail, and just brings them together. So we make unique a shape model, a specific one, instantiate the thing, pass the things that you received, and store it in our pimple. Great. So now you can give me a circle, you can give me some OpenGL drawer, I can put this into the shape, it will work. Okay, we cannot use it yet, so let's add a draw function, which basically just doesn't do anything but call the virtual draw function inside, in this shape concept class. Just a virtual dispatch, but hidden inside. You don't have to worry about this yourself outside. And then, because I want this to be a value, yeah, we definitely have to take care of the rule of 5. Copy operations, move operations, potentially even the destructor, depending on what we do. That is important. And it really is important. I should mention that it's supposed to be a value. If you move from an object, by default, you leave an empty object, a null pointer, which is great for a pointer, but not for value. So you'll definitely have to put a little more thought into how to model this value, this abstract thing, this wrapper class. The copy operations, I think this is quite reasonable. You will need a couple of clone functions in the shape concept. Not showing it, just mentioning it. But with this in place, we now pretty much have a value wrapper. Nice. Wasn't so much work, and it's pretty canonical, pretty idiomatic to some extent. It's always the same piece of work. But this shape abstraction, this now can do pretty much exactly what the shape base class could do before. Same capabilities, same power. But, and this is what C+ programmers again like to hear, it may be a little faster. Oh, and I know you're gonna need proof of that. It's a value, so it can be copied, it can be moved. It feels like any other value. And so it's simple. It's way simpler, and in particular, the surrounding code. The surrounding code is simpler. All of the complexity has been hidden inside this one class. This is what we call type erasure. So now, of course, again, the reaction is, that's not what I should do? Seriously, Klaus? Again, unfamiliar. But let me prove that the surrounding code is a little nicer by just showing it. So again, we have circles, squares also. See, no base class, no complexity, no virtual functions. Very straightforward code. Nice. Then again, we have a vector of shape values, not pointers, unique pointers or raw pointers, whatever, just values, which is more natural, nicer, easier to use, and there's hardly any potential to do something wrong. Then, factories. Well, this was one create function. We actually could think to implement this by means of std function, which is just another example for type erasure, but one that I don't write, but one that the standard library already provides for me. Nice. So this thing is the thing that gives me a vector of shapes. Draw all shapes. Okay, it's just a for loop again, but there is a dot. There's a dot, not an arrow. So we are using a value here, not a pointer. Then create and draw shapes. Okay, pretty much the same. But here, OpenGL drawer. No base class, no virtual functions, very straightforward code. And yes, exactly, that's the same thing that we've seen in the variant solution before. The same piece of code, just now reused, kind of. Same for the Your Shapes factory. Just the same thing. No base class, but a value. Same thing as before, in a variant context. Also, again, note, you're not allocating anymore. You just create a circle and you open GL drawer. Sure, inside the value. There may be an allocation. They don't have to be. There are optimizations to avoid that too. But you are totally unconcerned. You just create these values. And then in the main, you just put this all together again. Good. So, all together, so one more time, no pointers, no allocations, values everywhere. And so, again, the question, can we now separate work? Can you do your stuff or I do mine? Absolutely. Again, I just introduced this architecture boundary. We try to introduce a rectangle, and you would do this. You. I would be totally not interested in that. You would add your rectangle in your part of the code. You would also update your OpenGL drawer, just introducing new function. I don't care. I don't have to extend an interface for that. You can do this. Your shapes factory. Okay, so now you also deal with rectangles. It's a little piece of code, easily added. And again, I don't care. Nice. So we can now work together, which is, as you know, hopefully realize, pretty much the same as we had initially, the object-oriented solution. But just so much better, so amazing. Changes, extensions, pretty much work as expected, as initially. That's why you and I can work together. Every architecture boundary is probably a tier 2. Yeah. Your code, my code, clear separation, so it is an architecture. There were way fewer pointers. I don't claim there's none. I think there was none on the slide, but of course, somewhere inside are pointers, inside shape, for instance. There are definitely fewer virtual functions, absolutely, and they're hidden. Less inheritance and less manual memory management. Nice. And again, perhaps a little faster. Perhaps. Okay. Yeah, I know. You want to see some performance results, you get a couple of performance results. But again, only if you truly promise to not complain afterwards. Do you do this again? And I know by now the hand is getting more heavy, but yes. And else you again just close your eyes. Yeah, some people are doing this already. Thank you. Good. So, this was what we've seen before. Now, with type erasure, performance is, drum roll, okay. Yeah, I know. This is where people say, oh, Klaus, it's not as fast. However, I never said it's faster by a lot. Pretty much what we've done is we just put an inheritance hierarchy inside a class. So it should pretty much have the same performance characteristic, almost exactly the same, right? But it's now inside a class. Suddenly there are optimizations possible. Like for instance, we can use SBO, which is the small buffer optimization. For small objects, like strings do as well, we could just omit any dynamic memory allocation. And for big objects, then we might have to allocate. Which, in my test, actually gave me a little bit of extra performance. Which is, however, a program where I do not frequently create these objects. And so the potential here is massive. If you very frequently create these objects, do not do any allocation anymore, of course, performance gains are potentially vast. All right. So, of course, you're now asking, so let's get deleted. Should you now always use this stuff? Well, I kind of suggest that you do if you need object-oriented programming capabilities or architecture properties. But, of course, please do not forget about the other side, the functional programming solutions. They are absolutely amazing as well, just for different problems. And so now you're, of course, asking, when should I use the functional thing? When should I use the object-oriented programming? Well, it again boils down to the comparison that we've seen before. So, yeah, that's the answer nobody wants to see. It depends. Variant, more the functional programming approach, type ratio, more the object-oriented property. And again, on the function programming side, you have a fixed set of types, but an open set of operations. Whereas the type ratio does exactly the opposite. You can give me any shape, you can add one in the future, I don't care. So you have an open set of types, but right now in my solution, I can only draw. Yeah, we would have to change the wrapper, would have changed the expectations if we wanted to add an operation. So the variant is something that I would use best in lower levels of the architecture. And this is where function programming works really well. Algorithms. It's not something that you use high up, this is something that you use in the details. Variant works very well on those levels. But as the higher you go up, the better is probably you to use some object-oriented programming. Yeah, this has shown just to work well. But this is then where type ratio might just be a drop-in replacement for any kind of inheritance hierarchy. And so I consider these two solutions as the same thing, two sides of the same coin. One side of the coin is this object-oriented programming style, type ratio. And the other side is the function programming approach with a stood variant. But now, my idea is not that, take a coin, flip it, and just pick whatever the coin shows. That's not the idea. It may be a nice mental image to show, yeah, it's the same thing, just different. But here's the first rule of software design. So think about the architecture properties of a solution first. What do you want to achieve? How does the code evolve? How should it evolve? What do we need in the future? How do we provide extensibility? Based on that, you choose. But there's more. Yeah, you might have heard new standards on the horizon, C+26. Andreas Tedesco called this the next big thing. You might know what I have in mind here. He was talking about reflection. And yes, of course, this is where C++ developers get wet eyes when they just think about this. Reflection. And it actually will be pretty beautiful. It will be really powerful. The type ratio wrapper that I've shown you is something that you might just be able to generate with a reflection approach. So you might not have to write this yourself. You might just be able to let this generate. And the variant approach might actually also be obsolete at this point. There are better solutions once we go to pattern matching. But this kind of makes me afraid that, again, we have the one silver bullet solution, right? And I'm pretty much concerned that for some time everything will be about reflection, and then people actually start to think, oh no, this is not where it works. Oh, this is also a bad application. So, second rule about software design, always consider both the advantages and the disadvantages of a solution. So think about them first. And think, pretty much Titus said a very similar thing. So, first thing, where can I not use this thing? And then don't use it for that purpose. The other solutions might be better suited. All right, so to summarize, there is no silver bullet. Unfortunately, you have to know several solutions, good solutions, and choose from them, absolutely. And there are always pros and cons. There are always advantages and disadvantages. And you should know them. Yeah, you should really be aware what architectural properties do these things have. And so through this, it depends, which is kind of the difficult part, but it's the fun part. And this is what makes us software developers, to know these things and to choose the right solution. Okay, thank you very much.
So thank you. I take one from the online audience.
Of course.
So Xavier is asking if you know any library that helps with the boilerplate.
Yeah.
For instance, Microsoft's proxy, if you had a look.
I don't know that one, but I do know 3 libraries that actually might be a little bit of help. I'm personally not convinced that they're a lot of help, but perhaps a little. So you might know Ludion's Dino library. That one is nice. It doesn't reduce a lot of code, but perhaps it gives you an approach, the ability to do this a little more structuredly. Then there's the Zoo library by Madrid, Eduardo Madrid. This is a very powerful library, but there is a flaw. There's no documentation. Yeah, and I have told him so many times, write a docu, people will use that, people will love you. He doesn't write documentation. He did not write the documentation yet. And there's also, of course, Boost type erasure, which is the oldest one. Yeah, it's older than John Perrin's talk, I believe. This may be from 2005 around. I think it's a little complex, very generic, and so I'm not really certain if this would help. So right now, today, I would say, write it yourself. It's not an awful lot of code, but eventually, perhaps in 26, 27, perhaps then Reflection is ready to generate this stuff. And I think this may be the solution after all.
Another one from Marcus. In my opinion, C++ concepts have the potential to partially relieve the tight coupling for the functional programming version of the code. Did you try applying concepts to your design?
Concepts are inherently template-based. So yes, you can use concepts, but then you're again in this template header library. It doesn't solve the problem, but it improves things. Absolutely, because I should actually say what I'm expecting. Yeah.
Hi, I have such a question. There is this CRTP pattern, curiously returned,
Yep.
which is for sure not modern C++. It is older than Gang of 4. What do you think about using that in part of your design?
So I've actually talked about this today in my other talk, in length, so for half an hour. So it is not a drop-in replacement for inheritance hierarchies. It cannot be, because it pretty much takes away the nice properties. You don't have a common family of types anymore. And it also very, very quickly pushes you into the realm of templates only. And this actually has happened in big projects. People were very enamored with performance, thought this might be the solution, and they ended up with templates everywhere. Compile times were just miserable. And so, no, I don't think that CRTP is a general solution to get rid of that. Of course, if you have a compile time problem, sure, go for it. But generally speaking, you might need some dynamic polymorphism in many places as well.
Okay, thanks.
All right. Then, thank you very much, and have a great evening.